Welcome to the aerodynamics lecture again, right? Today we will discuss about the substantial derivative, path lines, then streamlines and streakline, right? That is the agenda for the today's class. We had a discussion on the continuity equation, momentum equation, energy equation in the last classes. Now we will be discussing the substantial derivative. So let us start with the acknowledgement to fundamentals of aerodynamics by John D. Anderson, and then this is the substantial derivative. So let us consider there is a fluid element. So we know this is a fluid element, and it is moving through a flow field, right? And say at time t1, it is at this particular location, and at time t2, it moved to another location, right? So we can say that there is a change in velocity, a change in location, and a change in the fluid element with respect to space and time. That is what our discussion in the substantial derivative. And say let us write the velocity field, right? The velocity acting on the fluid element, and let us say the velocity field V can be written as Ui plus Vj plus Wk. See, you already know what is the velocity field, what is the scalar field, what is the vector field, what is the scalar field, and all those things we have discussed already. So the good thing is, like, I want to discuss one by one. So we have made the basics sometimes back, and now this is also another basics to apply to the basic flows in the later stage. So we already know V is equal to Ui plus Vj plus Wk. Here the component U itself can be defined as U of x, y, z and time t. That is what the point here. So here you see the x, y and z, and it is represented by ijk vectors, and the time t1 and t2. So u can be represented as u of x, y, z and t. Similarly, v can be written as v of x, y, z, t, and w can be written as w of x, y, z, t. Again, in addition, we can have the term density. Say it may not change for the incompressible flow, but it is necessary to consider the density x, y, z with respect to the time t, right? Now, let us say if I consider the density at point 1, right? So density field at point 1, so let us say at point 1, we can write rho 1 can be written as rho of x1, y1, z1, t1, right? So if you say the fluid element at point 1, the fluid element moves to the point 2, right? So moves to the point 2. Then at the point 2 is some later time point 2, right? So we can now say at a new time t2, then we can define rho 2, that is equal to rho of x2, y2, z2, t2, right? So this is the change in density at a time t1 and t2. Now Okay, we will go to the basics of the Taylor series. Let us say rho is equal to rho of x comma y comma z comma t, right? So let us expand this using Taylor series, right? Expand this function in Taylor series. Right? So we know, right? So I want to write row 2 and I need to explain it in terms of row 1 plus there is a change in density dou rho by dou x at location 1 and we can write x2 minus x1 plus dou rho by dou y y2 minus y1 plus dou rho by dou z at 1 z2 minus z1 plus we can write dou rho by dou t at 1 t2 minus t1 plus other higher terms, right? We can keep on writing this in the higher order terms, right? We can expand it to any extent. Now, say I would like to divide this equation by t2 minus t1. That is the difference in time, right? So what I will do is like I take this row 2 minus row 1 by t2 minus t1. So please try to follow this equation. Okay. Say I would like to ignore the higher order term, right? Ignore the higher order term and write the other terms. So I can write dou rho by dou x of 1. So here it is x2 minus x1, x2 minus x1 by t2 minus t1 plus dou rho by dou y at 1 y2 minus y1 by d2 minus t1 plus dou rho by dou z at 1 z2 minus z1 by t2 minus t1 plus dou rho by dou t1. This t2 minus t1 by t2 minus t1, so this become 1. So I don't write that. Okay. So first we will consider this left-hand side equation, right? What is this left-hand side equation? Rho 2 minus rho 1 by t2 minus t1. So what is this term? This term is the average time rate of change of density of the fluid element from point 1 to 2, right? So we can write this left-hand side of this equation. Say I just write the limit t2 tends to t1. We can write rho 2 minus rho 1 by t2 minus t1 that can be written as d, the capital D I use, d rho by dt. So this d rho by dt is the symbol for the instantaneous time rate of change of density of the fluid element as it moves through the point 1, right? As it moves through the point 1. So we call this this symbol of d by dt as the substantial derivative. Now, we have defined this as a substantial derivative, right? So, the d rho by dt is the time rate of change of density of a given fluid element as it moves through the space. So, let us fix our eyes locked in the fluid element as it is moving, and we are watching the change in density of the fluid element, right? Like we are looking into the fluid element, right? So yes, yeah. Can you hear?
Yes, sir. You're audible, sir.
Yeah. So this is what the substantial derivative. Now let us say this d rho by dt and dou rho by dou t at point 1 is different, right? So dou rho by dou t is the time rate of change of density at a fixed point 1, right? At a fixed point 1, right? So for dou rho by dou t at 1, we fix our eyes at the stationary point 1 and watch the density change due to the various fluctuation, right? But d, the capital D rho by dt is the time rate of change of density of a given fluid element as it moves through the space. So let us come back to the equation. We have this equation, right? In this equation, 1, we have written rho 2 minus rho 1 by t2 minus t1. Now, by considering the limit, say limit, okay, as I say, the limit t2 tends to t1, the x2 minus x1 by t2 minus t1. What is this? This is almost equal to u velocity. Similarly, if we write limit t2 tends to t1 and y2 minus y1 by t2 minus t1, this is equal to v velocity. And similarly, the limit t2 tends to t1, z2 minus z1 by t2 minus t1, that is equal to w velocity. So this equation 1, now I will write this equation. How I can write this equation? The left hand side of the equation is already the substantial term d rho by dt, that is equal to, what is this? This is u term, v term and w term. So I write this as u into dou rho by dou x plus v into dou rho by dou y plus w into dou rho by dou z plus dou rho by dou t, right? So this is what our equation is, right? So we can now obtain the expression for the substantial derivative. What is the expression for the substantial derivative? we can say d by dt is equal to dou by dou t plus u into dou by dou x plus v into dou by dou y plus w into dou by dou z. Now, say in the Cartesian coordinate system, we can have the vector operator del, right? When we write this vector operator del to express this term, say, okay, I will write that also. So the del can be represented as I into dou by dou t, dou by dou x plus j into dou by dou y plus k into dou by dou z. Now, finally, we can write the equation d by dt is equal to dou by dou t plus v dot del. Right? V dot del. So now, if I consider, say, the assume that the flow field variable is a temperature. So if the flow field variable is a temperature, then I write like this: d t by dt, that is equal to dou t by dou t plus v dot del into t. It means we can write dou t by dou t plus u into dou t by dou x, v into dou t by dou y plus w into dou t by dou z. So here we need to note that the dt by dt is the substantial derivative. It's the substantial derivative and this dt by dt is a local derivative. And v dot del into t is the convective derivative. Right? So that is all about the substantial derivative. Substantial derivative is a sum of local derivative and convective derivative. So usually in the Anderson, he used to say some analogy in terms of some stories, right? So he says something like, you can imagine you are hiking in the mountain, okay? And in the mountain, you can find one small cave and you are about to enter inside the cave, okay? Now your body consists of, your body has a temperature already, right? And the temperature inside the cave is cooler than the outside, okay? So you are a fluid element now. So when you just walk through the mouth of the cave, you will feel the difference in temperature, right? Say it is almost like when you enter inside a shopping mall, right? Inside it is air conditioned and outside it is atmospheric temperature. And when you are entering inside, so when you enter inside the cave, there is a change in temperature, right? You feel the difference in temperature. That is analogous to the convective derivative. So you enter inside and you feel that with respect to all this space, you are feeling the change in temperature. That is analogous to the convective derivative. Now, what happens is when you enter inside the cave, someone throw a snowball to you, right? Someone throw a snowball to you. That snowball makes your temperature to change, right? You will feel the difference in temperature because of the snowball, right? So this temperature drop due to the snowball is termed as the local derivative. So the net temperature drop, I will ask you, the net temperature drop on you is because of the cave temperature, right? The cave temperature and the snowball temperature. That is what it is, total derivative or substantial derivative. How much temperature change in your body when you are inside the cave? First one is because of the convective derivative, and another one is one of your friends throw the snowball. By that way, the temperature is reduced, and hence the total is the snowball and the cave. So this is the substantial derivative, which is the summation of local derivative and the convective derivative. So all our equations like continuity equation, momentum equation, energy equation can be written in terms of the substantial derivative. So I recommend you to think about it, and you try to change our fundamental equation, that is continuity equation, momentum equation, and energy equation in terms of the substantial derivative. That's all about the substantial derivative, right? So it is possible to change the continuity, momentum, and energy equation, right? I will note it. Continuity, momentum, and the energy equation can be expressed in terms of the substantial derivative. All right. So please try it and get back. Okay. So I will continue this again, right? So this is what our discussion from point 1 to 2, the fluid element is moving, and we consider the velocity vector, velocity field in a vector field. V is equal to uy plus vj plus wk. Then uvw we have expressed in terms of x, y, z, and t. In the similar way, we can express the density rho, and based on the Taylor expansion, we can write rho2 is equal to rho1 and so on. By neglecting the higher order term, we can express the substantial derivative, and based on the substantial derivative, and then we have two terms. One is local derivative and another one is convective derivative. And we had a discussion on the analogy based on the hiking in the mountain, right? Entering into the cave and the snowball. That just you need to remember. Now we will discuss about pathline, right? Normally, whenever we do some analysis, we used to say where the flow is going, how the flow is going, and where the flow is going. So if you want to answer this question, we can draw the diagram of the path lines, streamlines, and then we can describe, oh, this is the way the flow is going, right? So let us consider an unsteady flow, right? Here, let us consider an unsteady flow. And there is a fluid element 1, okay? And this fluid element, say even in the unsteady flow, we have V can be expressed as V of x y, z and t. Because with respect to t, if some variable changes, then it is unsteady flow, right? So let us consider the element A and the element B at point 1 and point 2. Okay. So in an unsteady flow, the element A takes this path. Say at the later time t2, the location of the element A is here. Element B takes another path and its location is here. This normally happens in the unsteady flow, right? Path lines for two different fluid elements passing through the same point in space, right? So both of the fluid element passes through the same point, but it moves in a different path. Why it moves into a different path? That is because of various reasons. So the pressure difference and other local phenomena that we will understand little later, right? So here the velocity field can be defined as V is equal to V of x, y, z and t. Right? And we have already traced the path, right? So the path line for the element A and the element B is now traced. Okay. Now, say we can have the definition. Okay. So this is the path line, right? Okay. Then we need to go to the streamline. What is streamline? Right. So this is an airfoil. Right. So the airfoil and there is a fluid flow. Now, the definition of the streamline is a curve whose tangent at any point is in the direction of the velocity vector at that point. Say this is the velocity vector at that point, right? So if you draw a tangent, right, then it is in the direction of the velocity vector at that point. So these are the streamlines which we can draw around the aerofoil. So with this basic definition of the streamline, right? Now there is a question I will ask. If the flow is steady, okay. If the flow is unsteady, in this case, if the flow is unsteady, the fluid element A and B passing through the same point follows the different path because the path is unsteady, the flow is unsteady. Now the flow is steady, let us say, for a steady flow. So for a steady flow, the streamlines and the path lines are same, right? So you see there is a streamline passing through this and the same is a path line also, because the definition of streamline is the curve whose tangent at any point is in the direction of the velocity vector. So it is in the direction of the velocity vector if you draw a tangent. And this case, for a steady case, this is again, right? This is again in a steady flow, the streamlines and the path lines are same. Now, let us think a little and have some derivation. Now, for a given flow field, we want to write the mathematical equation for a streamline, right? So let us say, and the streamline shown in this particular diagram, right? We have a curve in space, and we also know that this is in terms of x, y, and z, right? So let us get to the equation. Let ds be the small or elemental it's a small element, right? ds is a small element in the streamline, right? And the velocity here is v, right? And v is parallel to the streamline and parallel to the ds, right? ds is the element of the streamline and v is the velocity which is defined, and v and ds are parallel. So we can have the cross product. Let us say the vector cross product ds cross v is equal to 0, right? So you can also go through the cross product and the other definitions. So ds cross v is equal to 0, and this equation is the valid equation for the streamline, right? This is the valid equation for the streamline. Now, to have more understanding, we can define this ds. So how to define ds? dx I plus dyj plus dzk. Similarly, v can be written as ui plus vj plus wk. So can we calculate the ds cross v? How to do that? Let us write I, j, k, and here we have dx, dy, and dz, and here you have u, v, and w. So this can be further expanded, say I into the w dy, I into w dy minus v dz plus j into dx w, or we can say, since we have included plus, we can write in the other way, u dz minus w dx plus k into, again, v dx minus u dy. So according to our definition of this streamline, we can equate it to 0. So the vector is given in this equation, right? So it is equal to 0. Then we can write these components like w dy minus v dz equal to 0, u dz minus w dx equal to 0, and v dx minus u dy is equal to 0. So this is the set of equation. This is the set of differential equation for this streamline. This is the differential equation for the streamline, right? So we know u, v, w as a function of x, y, z, and we can integrate and we can have the equation for streamline f of x, y, z equal to 0. So let us have further discussion on this, right? So this equation, say, okay, we will take this equation. V dx minus U dy is equal to 0. So one can write this equation as dy by dx equal to V by U. So this is the differential equation for a streamline in 2D case, right? Right. So again, I would like to have this streamline. We know a streamline, a single line which passes through the fluid, I mean, where the fluid element passes, and we have accommodated that ds cross V, and finally we got a set of differential equation. So we found the equation for the streamline, and similarly we can have this as dx by dz equal to U by W, and similarly this also we can obtain like this, dy by dx equal to V by U. Now, how we can obtain this dy by dx equal to V by U? So this is what this equation. So this is the streamline, and we have defined y is equal to f of x, right? And then you have a u in x-axis and v in the y-axis for a two-dimensional case, and v is a velocity vector, and we can define the slope dy by dx equal to V by U, right? So this is the equation of a streamline in the two-dimensional case in the Cartesian space. Now, I would like to recommend one phenomenon called stream tube. Streamline is a single line where the stream tube, say, let us say a curve C. Here you have a curve C. And in the curve C, there are a lot of streamlines which is passing through the curve C. It is almost like our hose in the garden, right? We have a hose in the garden, and the hose looks like this, and the water flows. So we can say that that hose pipe is the stream tube. And the stream tube, which is having many number of streamlines on the surface, or the curve C, which creates a tube called stream tube, right? So we will have the application of the stream tube in the later discussion, right? Now we need to know what is stream tube. Stream tube comprises of many streamlines on the curve C, right? So stream tube in the three-dimensional space is shown in this figure, right? Okay, one more point left, that is Streakline. Yeah, okay. Yeah. So this is the Streakline. Usually, the definition for the Streakline is that the streaklines are the locus of the fluid elements which have earlier passed through the prescribed point, right? So that is the definition. Streaklines are the locus of the fluid elements which have earlier passed through the prescribed point, right? So it also has some application that we will see later. Say this, say let us consider in this diagram, right? You have a fixed point 1, right? Then assume that the fluid elements that are passing through the point 1 over the given time interval T1, T2 minus T2, T1, T2 minus T1 is the time interval, right? So these fluid elements are connected with each other, right? So like the ants which pass through in a particular place, right? It takes a particular path, right? So here, if you see, consider an element A, and this element A is the fluid element that passed through the point 1 at a time t1. And element B is the next element which passed through the point 1. Similarly, C is the element that passed through the point 1 just behind the B. Like that, you can write all the fluid elements, right? So it shows that all the fluid elements that have earlier passed through the point 1 over a time interval T2 minus T1. The line that connects all these fluid elements is called the Streakline. Right? So, okay, so I will show one example of the Streakline. It is almost like you might have done a Reynolds experiment in the fluid dynamics lab. I don't know whether you have done that experiment, but I can say that whenever there is a fluid flow, right, the fluid is flowing like this, and assume that you are passing a die, right, and the die which can take the shape, and from that die we can draw the curve, Streakline curve, which is expressed like this. So this is there is a die passed through, and here you have a circular cylinder, and that creates the vortices. It is called the Karman vortex sheet, right? And this kind of trace, right, connecting all the fluid element, right, connecting all the fluid element, we can express this Streakline. So I stop at this point, right, with the definition of Streakline. Thank you very much.